begin our exploration of atomic structure by understanding what an atom truly is. Every element in the universe is made up of the smallest particles called atoms. The term atom comes from the Greek word atomos, meaning not to be cut, reflecting the idea that atoms are indivisible. Democritus was the first to suggest the existence of atoms, coining the name atomos. Over time, scientists have built upon this concept, leading to our modern understanding of atomic structure. As we move forward, we'll see how these tiny particles form the foundation of all matter. In 1803, John Dalton developed a groundbreaking theory of atoms. Dalton proposed that atoms are the smallest, dense and hard indivisible particles. Each element consists of a specific type of atom, and the properties of elements differ because of the kinds of atoms they contain. Dalton's theory provided a solid foundation for the laws of chemical combination, explaining why and how atoms combine to form compounds. However, as science advanced, certain limitations of Dalton's theory became apparent, which we'll discuss next. Dalton's atomic theory, while revolutionary, had its shortcomings. It couldn't explain why atoms of different kinds differ in valency and mass. The discovery of isobars and isotopes showed that atoms of the same element can have different atomic masses, and atoms of different elements can have the same atomic mass. Dalton also believed atoms were indestructible, but later discoveries revealed that atoms could be split into smaller particles. These limitations paved the way for deeper investigations into atomic structure. Late 19th century brought the discovery of various subatomic particles, such as protons, electrons, and neutrons. Scientists realized that atoms were not indivisible after all. R.S. Mulliken measured the charge on an electron using the all-drop experiment, finding it to be 1.602 times 1019 C. Out of all the particles discovered, electrons, protons, and neutrons are considered fundamental subatomic particles. This discovery marked a significant shift in our understanding of atomic structure. A.J. Thomson's cathode ray experiment in 1897 led to the discovery of the electron. William Crookes studied electrical discharge in partially evacuated tubes known as Crookes tubes. When a gas at low pressure is subjected to high voltage, invisible rays originate from the cathode, producing a greenish glow on the glass wall coated with phosphorescent material. These rays, called cathode rays, consist of negatively charged particles, electrons. This experiment was crucial in identifying the electron as a fundamental particle. Cathode rays travel in straight lines and produce mechanical effects, such as rotating a wheel placed in their path. They consist of electrons, which are negatively charged and travel at high speeds. Cathode rays can cause fluorescence, heat objects, and possess ionizing power, meaning they can ionize gases through which they pass. When cathode rays fall on heavy metals, X-rays are produced. These properties helped scientists understand the nature of electrons and their behavior. Charge-to-mass ratio, EM, of the electron was determined using variations in electric and magnetic fields. The value is 1.75882 times 1011 C/kg. This ratio is fundamental in understanding the behavior of electrons in different environments. The electron, being low mass and negatively charged, can be easily influenced by other electrons or positive nuclei. This property is essential in many physical and chemical processes. Proton was discovered by Eugen Goldstein in 1886 through the canal ray experiment. Protons are positively charged particles found in the nucleus of atoms. The experiment involved applying high voltage across a discharge tube with a perforated cathode, resulting in luminous rays extending from the cathode. These rays, called anode rays, were later named by Rutherford. The discovery of the proton further strengthened the atomic structure model. Anode rays, observed by Goldstein and named by Rutherford, travel in straight lines and are material particles. They are positively charged and can be affected by external magnetic fields. Anode rays also impact photographic plates and produce flashes of light on ZNS screens. The charge-to-mass ratio of anode rays depends on the gas present in the tube, being maximum for hydrogen. These properties help distinguish protons from electrons. James Chadwick discovered the neutron in 1932 by bombarding beryllium with alpha particles. Neutrons are neutral particles found in the nucleus of atoms, except hydrogen. Chadwick observed penetrating radiations unaffected by magnetic or electric fields, which consisted of neutrons. Neutrons are relatively massive and can penetrate the nucleus of any element, making them fundamental to atomic structure and nuclear reactions. Let's summarize the fundamental particles: electrons, protons, and neutrons. Electrons are negatively charged, protons are positively charged, and neutrons are neutral. Each particle has a specific mass and charge, and their discovery was pivotal in shaping our understanding of atomic structure. These particles interact to form the nucleus and the electron cloud, defining the properties of each atom. A.J. Thomson was the first to propose a detailed model of the atom, known as the plum pudding model. He suggested that the atom is a uniform sphere of positive charge with electrons embedded at various places, much like raisins in a pudding. While this model explained some aspects of atomic structure, it had significant limitations, such as not accounting for the movement of electrons or the distribution of mass. Thomson's model faced several drawbacks. The mass of the atom was considered to be evenly spread, and it was a static model, not reflecting the movement of electrons. This model couldn't explain the nucleus or the behavior of electrons in different energy states. These limitations led scientists to search for a more accurate representation of atomic structure, which brought us to Rutherford's experiments. Ernest Rutherford conducted the famous alpha scattering experiment by bombarding thin gold foil with high-speed alpha particles. He observed that most particles passed through without deviation, some were deflected at small angles, and a few were deflected by large angles. These observations led to the conclusion that atoms have a positively charged center, called the nucleus, with electrons revolving around it, much like planets around the sun. Rutherford's experiments showed that most of the atom is empty space, with a small, dense, positively charged nucleus at the center. Electrons revolve around the nucleus, similar to the solar system. The nucleus occupies only a tiny volume of the atom, but contains most of its mass. These findings revolutionized our understanding of atomic structure, setting the stage for further discoveries. Despite its successes, Rutherford's model had limitations. It didn't obey Maxwell's theory of electrodynamics, which stated that charged particles in motion should emit energy and eventually spiral into the nucleus. However, electrons in atoms don't collapse into the nucleus, indicating that another explanation was needed. This led to the development of quantum models of the atom. Atomic number Z is always equal to the number of protons in the nucleus of an atom. It also represents the number of electrons in a neutral atom. The mass number A is the sum of protons and neutrons, collectively known as nucleons. Atomic weight is the average of the weights of all isotopes of an element, considering their natural abundance. These concepts are fundamental to identifying elements and understanding their properties. Isotopes are atoms of the same element with the same atomic number, but different mass numbers. Isobars are atoms of different elements with the same mass number, but different atomic numbers. Isotones are atoms of different elements with the same number of neutrons. These variations explain differences in physical properties and behavior among elements and their forms. Isodiaphers are atoms of different elements with the same difference between the number of neutrons and protons. Isoelectronic species are atoms, ions, or molecules with the same number of electrons. These concepts help explain similarities and differences in chemical behavior and properties among various substances. Isotopes of an element occur in different percentages in nature, known as relative abundance. Using these percentages, the average atomic mass of the element can be calculated. For example, chlorine has two main isotopes, 35Cl and 37Cl, with abundances of 75% and 25%, respectively. This calculation is essential for understanding the properties and behavior of elements. Wave motion transfers energy from one point to another without moving matter. Waves are characterized by wavelength, frequency, time period, wave number, amplitude, and velocity. Electromagnetic waves, such as light, consist of oscillating electric and magnetic fields and travel at the speed of light. Understanding wave properties is crucial for studying atomic structure and the behavior of electrons. Electromagnetic spectrum arranges various types of electromagnetic radiations in order of increasing or decreasing wavelengths and frequencies. It includes cosmic rays, gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. All these radiations travel at the speed of light in a vacuum. The spectrum is fundamental to understanding the interaction of light and matter. Maxwell's theory explained the wave nature of electromagnetic radiation, but it couldn't account for phenomena like black body radiation, the photoelectric effect, and line spectra of atoms. These limitations led to the development of quantum theories, which provided a deeper understanding of atomic structure and the behavior of electrons. When light is dispersed by a prism, it separates into different wavelengths, forming a spectrum. There are two main types, emission spectrum and absorption spectrum. Emission spectrum occurs when a substance emits radiations after being excited, producing spectral lines. Absorption spectrum occurs when a substance absorbs specific wavelengths from white light, resulting in dark lines. These spectra are essential for identifying elements and understanding atomic structure. Max Planck introduced quantum theory to explain phenomena that classical physics couldn't. According to Planck, radiant energy is emitted or absorbed in small discrete packets called quanta. Atoms or molecules can emit or absorb energy only in integral multiples of quantum, not in arbitrary amounts. This theory explained black body radiation and the photoelectric effect, revolutionizing our understanding of atomic and molecular behavior. Photoelectric effect is the ejection of electrons from a metal surface when light of a certain minimum frequency, called threshold frequency, is incident. The minimum energy required to remove an electron is known as the work function. The maximum kinetic energy of photoelectrons depends on the frequency of incident radiation, not its intensity. This effect provided crucial evidence for the quantum nature of light. Niels Bohr developed a quantum mechanical model of the atom, explaining the stability of atoms and the emission of sharp spectral lines. Bohr's model proposed that electrons revolve around the nucleus in specific orbits, and energy is absorbed or emitted when electrons jump between these orbits. The angular momentum of electrons is quantized, being an integral multiple of h/2 pi. This model successfully explained the spectra of hydrogen and similar species. Bohr's model postulates that the atom has a central nucleus with protons and neutrons, and electrons revolve in circular orbits. Electrons can only occupy orbits where their angular momentum is an integral multiple of h/2 pi. Energy is absorbed or emitted as electrons jump between orbits, resulting in discrete spectral lines. The lowest energy state is called the ground state, and excited electrons return to lower orbits by releasing energy. Radius of Bohr's orbits and the energy of electrons in these orbits can be calculated using specific formulas. The radius increases with the principal quantum number, and the energy becomes less negative as electrons move to higher orbits. The total energy of an electron is the sum of its kinetic and potential energies. These calculations are fundamental to understanding atomic spectra and electron transitions. Ionization energy is the minimum energy required for an electron to leave the ground state of an atom. Separation energy is the energy needed to escape an electron from an excited state. These concepts are crucial for understanding chemical reactions, atomic stability, and the behavior of electrons in different energy levels. Bohr's model was successful in explaining the spectra of hydrogen and one-electron systems, but it failed for atoms with more than one electron. It couldn't explain multiple spectral lines, splitting of lines in magnetic and electric fields, or the uncertainty principle. These limitations led to the development of more advanced quantum models, such as the Bohr-Sommerfeld theory and wave mechanical models. Sommerfeld modified Bohr's theory by introducing elliptical orbits for electron paths and considering relativistic variations in electron mass. This theory explained the fine structure of spectral lines but couldn't predict the correct number of lines. It was a step forward in understanding atomic structure, paving the way for quantum mechanics. Hydrogen spectrum is an example of atomic or line emission spectrum. When hydrogen gas is excited, it emits light showing discontinuous line spectra, including Lyman, Balmer, Paschen, Brackett, Pfund, and Humphrey series. These spectral lines are important in astronomy for detecting hydrogen and calculating redshifts. Erwin Schrödinger developed the wave mechanical model of the atom in 1926. This model describes electrons as three-dimensional waves in the electronic field of the nucleus. The wave function, denoted by y, represents the amplitude of the electron's wave and can have positive or negative values. The probability of finding an electron is given by y2, and the space with maximum probability is called an orbital. Radial distribution function measures the probability of finding an electron at a certain distance from the nucleus. Nodes are regions where the probability of finding an electron is 0. Radial nodes depend on the principal quantum number, and angular nodes depend on the azimuthal quantum number. Understanding nodes is essential for predicting electron behavior and orbital shapes. Quantum numbers provide complete information about the size, shape, and orientation of orbitals. There are 4 types: principal quantum number n, azimuthal quantum number L, magnetic quantum number m, and spin quantum number s. These numbers are essential for determining electron configuration, ionization energy, and atomic radius. Principal quantum number determines the size and energy of the orbital. The maximum number of electrons in a shell is given by 2n2. As n increases, the size of the orbital increases. Each shell is designated by letters such as k, l, m, n, corresponding to n equals 1, 2, 3, 4 respectively. This quantum number is fundamental in identifying electron shells. Azimuthal quantum number, also known as orbital angular momentum, gives information about the subshell in which the electron is located. The value of L ranges from 0 to n1, and each value corresponds to a subshell, S, P, D, or the maximum number of electrons in a subshell is given by 4L plus 2. This quantum number determines the shape of the orbital. Magnetic quantum number proposed by Land gives information about the spatial orientation of orbitals. Its value ranges from L to plus L, including 0. The total number of orbitals in a subshell is 2L plus 1, and the number of orbitals in a shell is n2. This quantum number is crucial for understanding the arrangement of electrons in space. Spin quantum number was introduced by Uhlenbeck and Goudsmit in 1925. It describes the spin of electrons, which can be plusa or a half. An orbital can hold a maximum of 2 electrons with opposite spins. The spin of electrons is responsible for most magnetic properties of atoms, molecules, or ions. This quantum number is essential for understanding electron pairing and magnetism. Orbit refers to the circular path in which an electron revolves around the nucleus, accommodating up to 2n2 electrons. An orbital is the region of space with the maximum probability of finding an electron, accommodating up to 2 electrons. Orbitals have different shapes, such as spherical S or dumbbell-shaped P, while orbits are circular. Understanding this distinction is key to grasping atomic structure. Electrons fill orbitals according to the Aufbau principle, Hund's rule, and Pauli exclusion principle. The Aufbau principle states that electrons occupy the lowest energy orbitals first. Hund's rule says orbitals in a subshell are filled singly with parallel spins before pairing. Pauli exclusion principle states that no 2 electrons in an atom can have the same values for all 4 quantum numbers. These rules determine the electronic configuration of atoms. Electronic configuration of an atom describes the distribution of electrons among various orbitals. Most atoms follow the basic rules, but some elements like chromium and copper have exceptions due to the stability of half-filled and fully filled subshells. Symmetrical distribution and exchange energy contribute to the stability of these configurations, making them energetically favorable. Stability of electronic configurations depends on half-filled and fully filled subshells, symmetrical distribution, and exchange energy. Elements like chromium and copper exhibit extra stability due to these factors. Exchange energy is released when electrons shift positions within the same subshell, maximizing stabilization. Understanding these principles helps explain the behavior of transition elements and their unique properties. Wrap up: atomic structure is a fascinating journey from the indivisible atom to the complex quantum models we use today. Fundamental particles, electrons, protons, and neutrons, combine to form atoms, which are governed by quantum numbers and rules for electron configuration. The development of atomic models, from Dalton to Bohr and Schrödinger, has deepened our understanding of matter and its behavior. These concepts are the foundation of chemistry and physics, shaping the world around us.